Alright, so this is the second video in our electrolysis series. This time I just want you to start off by answering the first three questions. So can you please press pause, do the first three questions on page 12, and then press play when you are ready to see the answers. Okay, hopefully you did actually pause. First one, what ions are present in molten sodium chloride? Because you've got sodium, which is in group 1, you're going to have an Na plus ion. Chlorine's in group 7, you'll have a Cl minus ion. If you just wrote sodium and chlorine ions, you're not going to get the mark. You're asked for ions, you have to show me the charge. If you were to electrolyze it, what are you going to see at the cathode? So cathode is negative, remember panic, positive anode, negative is cathode. The positive sodium will be attracted to the negative cathode. When it gets there, it's going to gain an electron. So you're going to take your positive sodium ion, you're going to give it the electron it lost back, and when you do, it's going to just form normal sodium metal again. Because it's gaining an electron, we say it's reduced. Because metals are solid, you're going to see that solid build up around the cathode. What's going to happen at the anode? Well, you've got a negative chlorine, which is going to be attracted to the positive anode. Don't stop there. What happens to that ion when it gets there? It's going to be oxidized, all right? So it was negatively charged, means it had gained an electron. Take that electron away and it's going to become neutral, which is what you want. Just remember that when chlorine is a neutral element, it is diatomic. It's present as Cl2, so you're going to need to do 2 chloride ions, each of them losing 1 electron to give you Cl2. Because chlorine's a gas, you are going to see fizzing. Right, in the previous video we looked at molten ionic compounds. In this video we are going to look at aqueous ionic compounds. This is a bit harder. Just a reminder, ionic compounds, solid at room temperature. When they are solid, the ions are not mobile, they cannot conduct electricity. For electrolysis to work, you need to either melt your ionic compounds or dissolve them. When we melt them, we just say that they are liquid. When we dissolve them, we say they are aqueous. And in these states, the ions are mobile and they conduct electricity. Often it's dissolving that's used. Ionic compounds have very high melting points because of these strong electrostatic forces between oppositely charged ions in the giant ionic lattice. So it requires lots and lots of energy to melt them and to keep them as a liquid. Dissolving is much easier. So often we dissolve them, but this does pose problems, as we're going to see below. So if I look at my typical electrolysis setup, instead of having NaCl liquid, I've now got NaCl aqueous as my electrolyte. I've got the sodium ion and the chloride ion from the sodium chloride, but if I dissolve it in water and I introduce water, I'm also going to get H plus ions and OH minus ions from the water. So water itself can split up into these 2 ions. So instead of just having 1 positive ion migrate to the cathode, I've now got 2. I've got the sodium and I've got the H plus from water. Instead of having just 1 at the anode, again, I've now got 2. So please be aware that this is only applicable if it's aqueous. As well as saying aqueous, they might say in solution, but if they say liquid, if they say molten, there is no water present, and H plus and OH minus, they won't be present either. Okay, so only if it's aqueous or in solution. Now the separation of the ions is as we saw before. The positive go to the negative go to the positive. But when we are talking about what happens next, you're going to need to be able to choose between the ions at each electrode, as only one of them will be discharged. So we're not going to make sodium and hydrogen. You're going to have to choose and decide which one of these 2 elements we are going to make. So in order to choose at the cathode, you're going to need your reactivity series. I've written it out here. You don't need to learn it yet because I'll give it to you if it's needed for the quiz. We're going to revise this topic later in the term and then you can learn it off properly then. But I've written it out and I've circled the 2 ions that we're interested in. So we've got sodium ion and we've got a hydrogen ion, and we're trying to decide which one of these ions is going to be discharged to get back to the original element. Now this is my reactivity series, and as you go down the reactivity series, these guys are getting less reactive. But as they're getting less reactive, they're also getting more stable. Okay, think about it. Here at the bottom I've got silver and gold. Like, we use silver and gold in jewellery, we can wear it on our skin, it's not reactive, it doesn't harm us. If you've got something like potassium and sodium, these are really, really reactive metals. So they're more reactive, they're less stable. Down the bottom, they're less reactive, and they're more stable. Sorry, maybe that's not clear. More stable, less reactive. Alright, so when we're deciding which one is going to form, okay, we're going to be forming the one that's more stable, okay? Rather than turning Na plus back into very reactive sodium metal, we're going to turn H plus back into the much less reactive, much more stable hydrogen. So when we're describing what happens at the cathode, we're going to say that Na plus and H plus are going to migrate to your cathode. Okay, because opposites attract. But when they get there, this is the way we phrase it, but we're going to write that H plus is preferentially discharged. So I'm not going to remove the charge from both of them, I'm only going to remove the charge from hydrogen. So H plus is preferentially discharged because H2 is less reactive than sodium. So we're choosing to make the less reactive element, because remember, when we discharge sodium, as we did at the start of the lesson, you're discharging it and you're getting back to a very reactive sodium metal. So we're going to discharge hydrogen instead. Alright, so I'm going to take my H plus and I want to turn this back into H. I'm discharging it, I'm removing the charge. Okay, now when I turn hydrogen back into an element, hydrogen is diatomic, so I'm not going to turn it into a hydrogen atom, I'm going to turn it into H2. If I'm turning it into H2, I am going to need to discharge 2 hydrogen ions at the same time. It's got a positive charge, which means it's lost an electron, so I'm going to give it an electron back. But because I've got 2H plus, I'm going to need to supply 2 electrons in total. They both take an electron back, then they pair up to form hydrogen. Hydrogen is a gas, okay? So because it's gaining an electron, this is an example of reduction. So once again, we're seeing that the positive ions are reduced at the cathode, and because hydrogen is a gas, we are going to see bubbles. I want you to have a go at this yourself. If we come back over here to the questions, don't do 6 yet, just do 4, do 5, do 7 and do 8. So don't do the anode, just do the cathode, but do the cathode for 2 different electrolytes and see how you get on. So please do press pause and actually try this for yourself. Okay, hopefully you got the first one right, although I realise copper sulfate may have been a little bit difficult. Ions present in aqueous sodium chloride, we've just seen this, okay, you've got sodium and chlorine from sodium chloride, but the aqueous is going to give you H plus and OH minus as well. What's happening at the cathode? I mean, I've kind of just written everything you might need to say. This is probably too much, okay, but the Na plus and the H plus will both migrate there, but the H plus is going to be preferentially discharged because that means we're making hydrogen, and hydrogen is less reactive than sodium, so less reactive means it's more stable. If hydrogen, H plus, is being discharged, what happens? Well, it's positive, so you need to give it an electron to get rid of that charge. Because hydrogen as an element is diatomic, I'm going to be forming H2, which is a gas, and I'm going to see bubbles. Also just mention that it's reduction. Okay, I know you've given a half equation, just spell it out for the examiner that gaining electrons means reduction. And the next one I asked you to do was the copper sulfate one. A little bit harder. You do need to know that copper has a 2 plus charge. I know it's a transition metal, but you need to know it. It's got a 2 plus charge, and then sulfate is SO4 2 minus, so it's one of your polyatomic ions. Again, because it's aqueous, you're going to have H plus, and you're going to have a OH minus. So at the cathode, again, the positive ions are going to migrate there, Cu2 plus and H plus, but Cu2 plus is going to preferentially discharge. If I just show you again my reactivity series, you'll see copper is lower than hydrogen. That means copper is the more stable, less reactive one, and that's the one that we are going to try to form. So if copper is forming, copper's got a 2 plus charge, that means it's lost 2 electrons. Give it the 2 electrons back and it forms copper metal. Metals are solid, so you're going to see copper solid build up on the cathode, and again, just spell it out that at the cathode it is going to be reduction. Right, we're going to have a look now at what happens at the anode. So you'd probably say the anode was a bit easier because there's a rule: the halogen always forms. So if you have like sodium chloride, sodium bromide, sodium iodide, if you've got a halogen present, then the halogen is always going to be discharged over OH minus. Your exception is if you've got sulfate. So we do like copper sulfate. If you don't have a halogen, then the OH minus will be discharged and oxygen is going to form. So when we had our sodium chloride aqueous, our two negative ions were Cl minus and OH minus. They both go to the anode. Cl minus preferentially discharged. And then you'll write your half equation for chlorine, just like we've done already, and you'll say you see bubbles. If you have copper sulfate aqueous, which we have in our other question, then your negative ions are OH minus and SO4 minus. I don't have a halogen, and in this case it's the OH minus that gets discharged. So I've written that out here, okay. OH minus preferentially discharged. The half equation is quite tricky to write, and it did come up last year. Okay, so you're starting off with an OH minus, and I want to discharge it. I want to remove the charge and turn it into neutral products. But here we've got two elements. I've got oxygen and I've got hydrogen. Now we do form oxygen, okay? That's why we see the bubbles and we see the oxygen. So oxygen at room temperature, as an element, is going to be diatomic. So I'm going to form O2. O2 is a gas, so I am going to see bubbles. But I don't form hydrogen gas. I actually form water as my other product. So when I discharge this, I'm turning it into oxygen. So I see bubbles, it's a gas, but I'm making water. I am not making hydrogen. Now in order to do this, first of all, I'm going to balance the equation. It's not balanced. I've got two oxygens on the left and another oxygen there. So I've got, three oxygens on the right hand side. I've only got one on the left. Now if you were to put a 3 there, you have 3 hydrogens, but then you've got 2 hydrogens here, and there's no way to change the number of hydrogens without then changing the number of oxygens and making this 3 wrong anyway. So what we're going to do, and it's just because I know that this is what we do, I'm going to put a 2 here. Okay, if I'm going to put a 2 in front of the water, I'm going to make 2 equivalents of water, because when I do that, I've got 2 and 2 is 4 oxygens on the right. I've got 4 hydrogens on the right, and I can easily get 4 on the left by just putting a 4 in front of the OH minus. Now if we've got 4 of the OH minuses, they each need to lose 1 electron to be discharged, so I'm taking 4 electrons away in total. So this equation did come up last year. It was 4 2 marks. I would suggest just learning that equation off in case you're asked to reproduce it. Again, this is going to be an example of oxidation, and in terms of what we're going to see, you're going to see bubbles. Press pause, all right? Try and recreate this yourself. We've already gone through the examples, but please do 6 and do 9, and then press play for your answers. So starting with question 6, I'm looking at the anode for sodium chloride. So going to the anode, I'm going to have the Cl minus and the OH minus, but if you've got a halogen, the halogen always forms. So Cl minus preferentially discharged. Half equation is the same as what we've seen before. I can say Cl minus is oxidized, and I can say I see bubbles because it is a gas. Question 8, a little bit harder. Sorry, question 9, a little bit harder. Your negative ions in this case are SO4 minus and OH minus. We don't have a halogen, so I can't apply that rule. And in this case, the OH minus is going to be preferentially discharged. Much harder half equation to write. I would suggest just learning it off. You are going to form oxygen gas, so you do see bubbles, and to be fair, they really wouldn't ask you this, but if you looked at the structure of the OH minus polyatomic ion, the negative charge is specifically on the oxygen atom, so it's oxygen that's oxidized. Oxygen loses electrons, it's not hydrogen, so specifically oxygen is what is oxidized out of the two of them there. Very last question. Describe what occurs at the cathode and the anode when water is acidified with sulfuric acid and is electrolyzed. We've only been looking at splitting up ionic compounds, but you can, and it's a small part of the specification, they say you can also split up water. And the reason is because, as we've just seen, water contains OH minus ions and H plus ions. And if you add a little bit of sulfuric acid dissolved in water splits into ions, and those ions help the electricity to flow. So without the acid, water doesn't conduct electricity very well. You add in the acid, electricity flows, and the water, it encourages the water molecules to split into these two ions. Because it splits into those two ions, if we just look at what's going to happen at the cathode and at the anode. At the cathode, the H plus ions are going to migrate to the cathode. So the H plus ions migrate here. When they get to the cathode, they are going to discharge. Our equation for this, H plus, I need to turn it back to H. Hydrogen is diatomic, so I need two H pluses. They each gain an electron, and it turns into hydrogen, and I'm going to see bubbles. At the anode, it's going to be the OH minus ions that migrate to the anode. The OH minus is then going to discharge. We get O2 gas, we get two equivalents of water, and again, because of oxygen gas, we are going to see bubbles. Okay, often they just ask you what are the products at the cathode and the anode. If it's water, you get hydrogen at the cathode, you get oxygen at the anode. These are the half equations, though. If you go a little bit further, at both you will see bubbles. They could ask you to prove which gas is which. Hydrogen, lit splint, squeaky pop, and then oxygen, glowing splint, is going to relight in the presence of oxygen. So it's just one little point on the spec, but worth knowing all the same.